Again, the chaperones are important for many proteins to fold off the ribosome. So let's take a look at some of those chaperones. This is a very big, complex story, and I want to try to reduce it to the simplest possible terms, restricting ourselves in this discussion mostly to bacterial systems, realizing that that there are other prokaryotic systems, and there are certainly a whole different machinery in eukaryotes, but the bacteria give us a great overview of what this is all about. So molecular chaperones assist de novo folding, as I've mentioned, co-translationally, and also refolding in vivo. Remember, they were originally identified as heat shock proteins that were expressed as a result of the exposure of the organism to a heat shock, and the chaperones then allow the system to recover by allowing the proteins to refold. In this case, though, let's focus on de novo folding for a while. There are two phases of chaperone assistance. First of all, the interaction, as I've already described, with the short nascent polypeptides, a trigger factor in the case of bacteria. There are other factors in the case of eukaryotes. So the trigger factor is interacting with that nascent polypeptide chain, perhaps preventing it from forming incompetent structures, aggregates perhaps. There's another set of molecules that also interact with that nascent chain, the DNA K and DNA J complexes. These are known to hinder aggregation through a kinetic partitioning mechanism. So not only do they interact as the protein is coming off the ribosome, but also after release from the ribosome. They don't allow protein folding to proceed per se. Instead, they bind the unfolded protein, release it. The unfolded protein may then fold, or not, and in which case it comes back and binds again to the ribosome. So that's your kinetic partitioning. If the unfolded protein exists in solution, then it could aggregate and precipitate. So what the chaperone in this case does is allow that unfolded protein to prevent aggregation of that unfolded protein, so that it might then have a chance to fold to its native state. I've listed some other complexes that are important to eukaryotes. Not so important. Just I want you to remember that we can interact on or near the ribosome, and then later the chaperonins, the phase 2 set of molecules, come into play, and these complete the folding off ribosomes. So here what we see is that there's the trigger factor handing the nascent chain over to DNA K, DNA J then associating with that free protein off the ribosome and delivering it again via that kinetic partitioning to GRO-ES complex, which we'll describe again in a moment. And GRO-EL allows the non-native, prevents that non-native protein from partitioning out into the cytosol, where it can undergo again those aggregation events. Let's see, what else do I want to say about this? We're going to talk in detail about GRO-EL in a moment. Oh, I'm also pointing out that the eukaryotes have different systems, but we believe that they behave in similar fashion to the GRO-EL chaperonin system. Oh, I didn't complete my sentence here. Some large complex proteins have very specific chaperones or signals that determine what chaperones they interact with, and what their ultimate folded fate or maybe oligomeric state will be. One thing I'll say, and I think I say it again on another slide, is that the mechanism of GRO-EL induced or assisted folding is a little bit, it's challenging to interpret the literature, right? So there's evidence that the chaperonins behave just like DNA K, DNA J, that is to say, they bind and release unfolded protein and don't shepherd protein folding per se. There is other evidence to suggest that GRO-EL actually allows proteins to fold inside an internal cavity. Both situations have been observed, and you can easily understand how both prevent the formation of folding incompetent structures. But they're different mechanisms. So let's look closer at the chaperonins. Right. Some chaperonins engulf and fold non-native proteins. So here's a nice cartoon of this whole process. A non-productive intermediate is here, but we see between DNA K and DNA J bound to some unfolded protein. We deliver that protein via some intermediate molecules to GRO-EL, GRO-ES. We'll look at the structure of GRO-EL in a moment, but it's basically this double toroid with a cap. GRO-ES is a cap molecule, and we see that we've bound ADP, nothing's happening. We bind ATP, big conformational change, and perhaps a stretching of that unfolded chain. And then that conformational change allows for the actual folding of the molecule. Maybe we're incompletely folded at this point. Maybe there's some time dependence of this folding event, and then we release, right? And so we hydrolyze our ATP to ADP, and then we release. Maybe the protein is native, maybe it's still unfolded, in which we can go back again and perform this process. The key here being, and let me remind you that this species, free in solution, is prone to aggregation, and that's bad, right? So the chaperones are preventing that aggregation from taking place. It's worth noting that lots of proteins in bacteria, presumably even more in eukaryotes, require chaperone assistance for proper folding. In the case of the stressed system, right, not de novo folding now, but refolding, as many as 30% of bacterial proteins require chaperone assistance after heat shock. Again, eukaryotic chaperonins have different details, slightly different structures, and are less well understood. GRO-EL is the archetype of chaperonins, the bacterial system. And GRO-EL is composed of two heptameric rings, so that double toroid, and a heptameric cap called GRO-ES. And the cap can bind on one face or the other, depending on the ATP-bound state. There's a cavity inside GRO-EL that can accommodate proteins of up to 60 kilodaltons, perhaps even larger. Very large cavity formed there, whose structure changes depending on the nucleotide-bound state. There's work that suggests that the encapsulation of the protein, that unfolded chain, can accelerate folding by up to 10-fold. As I said, though, the literature is conflicting. So when you read your textbook, I want you to get the sense from my lecture that the story is more complicated. Nevertheless, what we see from crystal structure analysis of the chaperonins is that a difference occurs depending on the nucleotide bound state, right? So in this trans ring, we have ADP bound perhaps, or perhaps no nucleotide. And what we see in the cavity is that it's longer, it's narrower, and there's a very clear set of bands of hydrophobic side chains lining that cavity. Very easy to imagine in this trans ring an unfolded protein with exposed nonpolar surface area binding here, right? These are binding sites for unfolded protein. When we bind ATP, now the cavity structure changes dramatically, becomes much larger, and we have no clear patterning to our hydrophobic surface area anymore, and the protein can then fold. In some cases, as I've said, proteins do actually fold inside the cavity. That has been observed. You want to read more about this, go to the molecule of the month function feature there at the PDB. Remembering too that this hydrolysis of ATP gives us a timing here, right? As long as we have ATP bound and we haven't hydrolyzed, we're going to maintain this structure. When we hydrolyze, the cap's going to come off. We're going to release the protein. Maybe it's folded, maybe it's not, and still needs to go through another round of refolding. I wanted to show you this cartoon of the chaperonin GP31, gene product 31, from the bacteriophage T4. Now we're not looking at a bacterial chaperone, we're looking at the chaperonin from a bacterial virus. For those of you that aren't aware of the bacteriophage, they are bacterial viruses. They have their own chaperone machinery, and this is a great structure, right? Obviously a Nature paper, because they've determined a structure of the chaperone. Here you can see the two toroids, right? And then there's the GRO-ES analog, and you can see inside the folded protein, right? And on the other side you see the disordered protein. So it just so happens that this is a capsid protein that's been bound inside the cavity, and it's known to have a much more elongated structure. So this structure is consistent with what we know that capsid protein should look like. This is not. So what we see in the trans ring is an unfolded protein bound. You see our hydrophobic ring of interactions there again. And then in the cis ring with GRO-ES bound, or the GRO-ES homolog bound, we see the folded protein. It's worth pointing out that this kind of structure determination is not one that I've described to you before. This is called cryo-electron microscopy, and it's very useful for very large complexes of molecules. I don't think this is quite the place to go into it, but simply imagine that what's done is a two-dimensional crystal is formed by cooling an array of proteins very quickly, and then we use an electron beam to interrogate that two-dimensional crystal, and by averaging over many units of the crystal, we can build up a model such as this. And in this case, it's very easy to see how this structure correlates with the crystal structure that I've showed you.